So in the last class, we gave a proof of Galois theory. So today what I'm going to do is I'm going to give you one more examples to demonstrate the Galois theory. For that, we are going to use f is equal to q and k is equal to q of root 2 comma root 3 comma root 5. So definitely k is separable over f. Why? Because the irreducible polynomials that gives root 2, root 3 and root 5s are x square minus 2, x square minus 3, x square minus 5. And all the zeros of this polynomial are in k, and they have only their multiplicity of each zeros are 1. So k is a separable splitting field, finite separable splitting field of f. So let us take this as f of x. So f of x, this is probably equal to x to the power of 4 minus 5 x square plus 6 times x square minus 5. So when you multiply that, what do you get? X square, x to the power of 4 minus 5x square plus 6 x square minus 5 x6 minus 5x to the power of 4 plus 6x square minus 5x to the power of 4 plus 25x square minus 30. So it will x to the power of 6 minus 10x to the power of 4 plus 31x square minus 30. So the irreducible factors of f, the irreducible factors of f are x square minus 2, x square minus 3 and x square minus 5. And k is a separable splitting field of each of these. So we are going to start a definition here at the same time. Let f of x belongs to f of x, and k be the separable splitting field of every irreducible factors of f of x. So in here it is f of x is x square x to the power of 6 minus 10x to the power of 4 plus 31x square minus 30. Irreducible factors are this. So k is the splitting field and it is separable extension of q for this polynomial. That implies K is a finite normal extension of F. Then the Galois group K over F is called the group of f of x. So the group of f of x equal to x to the power of 6 minus 10x to the power of 4 plus 31x square plus 30 is the group of q of root 2 comma root 3 comma root 5 over q. Now what we are going to do is we are going to describe, we have done this for a smaller group, but we will do it for this one also. We are going to describe all the extensions of f ending at k, and we are going to describe all the groups and subgroups of the Galois group K over F. So let us start with the Galois group. So G over F, K over F is equal to, these are all automorphisms on K leaving F fixed. So what are the possible automorphisms on K leaving F fixed? Those automorphisms are determined by root 2, root 3 and root 5. Of course, the first one will be the identity map. That means root 2 go to root 2. Root 3, I will write it as a column like this. Root 2, root 3, root 5. I goes to root 2 goes to root 2. This one root 3, root 5. Then I am going to write sigma root 2, where root 2 is fixed and these are all changed. See, this has to go to a conjugate of, root 2 has to go to its conjugate, root 3 has to go to its conjugate, and root 5 has to go to its conjugate. Conjugates are root of, the conjugate of root 2 is root 2 and minus root 2. So sigma root 3 will be minus root 2, root 3, root 5, minus root 5. And sigma root 5 is going to be minus root 5, minus root 3, root 5. And we have some more that actually is fixing root 2 and root 3. So we'll call it as sigma root 2, root 3. So this will be root 3, root 2, root 3 minus root 5. Next one is root 3 comma root 5, where only root 2 is changed. Root 3 comma root 5. The next one is sigma root 5 root 2, where root 3 is changed. So root 2 minus root 3 root 5. And the last one is actually everything is changed. So we'll take it as sigma 0. That is minus root 2 minus root 3 minus root 5. So G over F contains 1, 2, 3, 4, 5, 6, 7, 8 elements. I sigma root 2, sigma root 3, sigma root 5, sigma root 2 root 3, sigma root 3 root 5, sigma root 5 root 2, and sigma 0. Those are this. So corresponding to each of this, so we are going to define now corresponding each of subgroups of this, we should have a fixed field that is an extension of f. So we will write the extensions of f. Extensions of f. One is q, because that is extension of itself, then q of root 2, then q of root 3, then q of root 5, then q of root 2 root 3, then q of root 3 root 5, then q of root 5 root 2, then the final q of root 2 root 3 root 5. So we have 1, 2, 3, 4, 5, 6, 7, 8 elements. So this is where you will define the map now. So lambda is like this, takes one element from here and it should go to lambda q. Lambda q will be, I'm not going to write lambda, so the lambda q will be what? Lambda q is going to be, see, every element of this, every automorphism fixes f. So q is actually mapped to the g of k over f. That is the whole set of automorphisms. Then we'll have here q root 2, q root 3, q root 5. So here q root 2, if you take q root 2, lambda of q root 2 is actually g of k over q root 2, leaving root 2 fixed. So what are the things you have here? This will be g of, or I will write it as, instead of writing the whole thing here, lambda, okay, we'll write lambda of q is equal to g over k over f. Your lambda of q root 2 is equal to, definitely I will be there because that is going to fix q root 2 always. Then sigma root 2, because that is going to fix q root 2. Then next one is sigma root 2 comma root 3 and sigma root 5 comma root 2. Similarly, see, I'm going to wipe this off. Instead of writing like this, let me write down q of k over f is equal to I root 2 sigma root 3 sigma root 5 sigma root 2 root 3 sigma root 3 root 5 sigma root 5 root 2 and sigma 0. So I'm going to take this out. So we'll draw the diagram here. The first one is, we'll write it from bottom. It is F is equal to Q. Then you have Q root 2, Q root 3, Q root 5. These are all extensions of Q. And you have Q root 2 root 3, Q root 2 root 3 root 5, Q root 5 root 2. And you have Q of root 2 root 3 root 5. So the Q goes straight to the G of K over F, and that is equal to I, the whole thing. I'm not going to write the whole thing there, but that is what is going to happen there. Now, Q root 2 should be, this is our lambda, Q root 2 should be going to lambda of Q root 2 is equal to G of K over Q root 2, and that is equal to I root 2 then root 2 comma root 3 sigma root 5 comma root 2. This has got 8 elements, this has got 4 elements. Similarly, root 3 will have, I'm not going to write that one, we'll have sigma of Q root 3 is equal to, you can fill it up, Q of root 5. That will be I comma etc. I comma etc. Like sigma root 3, sigma root 3 root 5, sigma root 2 root 3. That is here, and similarly here. This has got 8 elements. The smallest field has got the biggest subgroup. Then it has got only 4. This one, lambda of Q root 2 comma root 3 is equal to G of K over Q of root 2 comma root 3, and that is equal to, you have to fix both. So that will be, definitely I will be there, and sigma root 2 root 3. Just got only 2 elements and nothing else, because you have to fix both Q root 2 and Q root 3, right? Root 2 and root 3. Then similarly Q of root 3 comma root 5 will be I sigma root 3 root 5. Similarly same thing. So here this will be going to just I. So the biggest or the largest extension is going to the smallest subgroup, and the smallest extension goes to the largest subgroup. Now let us see how the Galois theory behaves on finite fields. So we know that every finite field contains p to the power of n elements, p to the power of r elements for some prime p and r greater than 0. And the elements of the field are precisely the zeros of the polynomial x to the power of p to the power of r minus x. We have established this result in the finite fields already. So let us consider a finite field. Let f be a finite field containing p to the power of r elements and k be a finite extension of f of degree n, and that is the degree of k over f is equal to n. And we also know that if f is a finite field that contains q elements and D is an extension of finite extension of f of degree n, then E contains q to the power of n elements. So we'll apply this result here. So K contains p to the power of Rn elements. And the elements are precisely the zeros of x to the power of p to the power of Rn minus x. So we have a k here and an f here. This contains p to the power of r elements, and this contains p to the power of r n elements. And what we are going to do is we are going to find out the automorphisms on this. So let us several automorphisms generated by the base fields of the vector space K over F. There are n elements there. So those are the base elements that determines the automorphism on K. So we are going to define our aim is to find out the characteristic of the Galois group of K over F when F is finite. So let us define an automorphism on K. Define an automorphism on K by sigma PR of alpha is equal to alpha to the power of p to the power of r for all alpha in K. So this definitely leaves F fixed, no problem, because the order of F is p to the power of r. So alpha gamma sigma PR belongs to the Galois group of K over F. Since sigma PR leaves F fixed. It's an automorphism on K and leaves F fixed. Now, let us see sigma of p to the power of r I of alpha. This is actually, you are composing sigma PR I times. When you compute this, you will find that this is equal to alpha to the power of p to the power of Ri. Because each one of this one is alpha to the power of PR, then when you compose it, you are going to get this. So, now alpha to the power of p to the power of Ri is equal to alpha for all alpha if and only if I is equal to n. Because, see, if you take a polynomial x to the power of p to the power of Ri minus x, the zeros of this polynomial are p to the power of r to the power of I elements in and they are all in the extension of f of degree I. So this contains only p to the power of I elements. So the small, even not the only if, say, for all alpha, not even only if, when n is the smallest integer, n is the smallest integer value for I. Because of this contains only p to the power of I elements, but we need to collect all the elements of K. Then only it will be all alpha in K. Sorry. Okay. So that means sigma to the power of p to the power of r n of alpha is equal to alpha for all alpha in K and n is the smallest integer satisfying this condition. Of course, you can have bigger than n, but this is the smallest one. What does this mean? This means that sigma to the power of p to the power of sigma PR to the power of n is equal to I, the identity map. How many elements are there in G of K over F? N elements. Why? Because the degree of K over F is equal to n and K is a finite normal extension of F. Why finite normal extension of F? Definitely K is a splitting field. Definitely K is a finite extension. And definitely K is a separable extension also. Because all the polynomials of K, p to the power of x to the power of p to the power of r minus x are distinct. Are distinct. So this is a finite normal extension of F. So that means g of K over F is equal to, the order of this is equal to the degree of K over F, and that is equal to n. And we found, we found a automorphism on on this Galois group. When it composed n times, it will become I. That means G of K over F is a cyclic group generated by sigma PR of order n. So G of K of F is cyclic of order n. So let us state that theorem one more time that we just now proved. So let F be a finite field with p to the power of r elements for some prime p and integer r greater than 0, and K be a finite extension of F of degree n, then the Galois group of K over F is cyclic of order n and is generated by sigma PR of alpha is equal to alpha to the power of PR, and that actually belongs to G of K over F. Let us do a problem on finite fields. So find the order and the generator of the Galois group of the Galois field of 729 over the Galois field of 9. See, this is a finite field of 3 to the power of 9. And this is a finite field of 3 to 3 square. Oh no, this is 6, I think. This is 6. This is 6. Okay. So in our earlier theorem, F is equal to G of Galois field of 3 square. That is, P is equal to 3, R is equal to 2. And K is equal to GF of 729, which is GF of 3 to the power of 6. So the N is equal to 3. Because this is 3 to the power of 6 and this is 3 to 3 square. So K is a finite extension of a finite field with the 3 square elements of degree 3. Extension is so this K over F is equal to 3. And that is equal to the order of K over F. And that is equal to the order of Galois group of GF of 729 over GF of 9. So that's the order. You need to find out the generator. The Galois group of G of K over F is cyclic with or generated by sigma P to the power of R 3 square of alpha is equal to alpha to the power of 3 square for all alpha in K. So the generator of GF of 729 over GF of 9 is sigma 9 defined by alpha is equal to alpha to the power of 9 for all alpha in GF of 720. So the generator is sigma 9, the order is